Beam control can be achieved using different methods. Some are physical, and others involve signal processing. Loudspeakers without manifolds or horns rely on directivity control by committee, or phase steering. At locations where the acoustic output of each individual element arrives in time relative to the others, they add. When the acoustic output relative to the others arrives enough out of time, there's cancellation. It's possible to modify the directivity with signal processing. However, with omnidirectional array elements, the spacing between them and the signal processing for each element needs to be properly implemented. This is not easily accomplished. When it's not, grating lobes can be unintentionally created. And side lobes can emerge in problematic locations. For modern articulated line array elements that use horns and manifolds for high-frequency directional control, we can rely on an intuitive and simple steering method. Point the speakers where you want the sound to go. Let's call this amplitude steering. The modern line array uses this property to create highly sculpted coverage shapes at higher frequencies. Amplitude steering becomes progressively less effective as the wavelengths become longer in the lower half of the spectrum. Phase steering is the dominant force for this range and presents a significant challenge. In its standard form, the coverage shape in these ranges does not track the sculpted shape of the higher frequencies. A single beam emerges that is typically aimed too low and often too narrow and variable in both cases over frequency. This leaves us with a complex yet limited challenge: reshape the lower range without reshaping or compromising the upper range. Active phase steering with specialized signal processing provides us with the capability of aiming and controlling the beam in new ways. This method is far less intuitive than simple amplitude steering, since we are bending the sound in directions different from where the speakers are aimed. In the low-mid range, there are virtually no level offsets between the individual arrivals. The phase offsets drive the coverage to narrow toward the center, phase steering. And the low-frequency coverage is narrowed to less than a single element. We can make an asymmetric coverage shape by employing a mix of splay angles between the elements. Small splay angles at the top of an array create deeper coverage in contrast to wide angles at the bottom. We can see that the high-frequency coverage closely tracks the differences in splay angles. And yet, lower frequencies do not follow the sculpted HF shape because the steering mechanism is not the same. How can we modify the low-mid beam shape with minimal costs and side effects? Let's first try amplitude tapering. We can turn down the level of the lower cabinets in the array. This will strongly affect the HF shaping, but only minimally affect the LF shape. This is a non-solution and comes with the cost of reduced headroom and dynamic range. One part of the system will limit before another. A less severe alternative is to taper only the mid-low frequency range with EQ. This is again only minimally effective and reduces headroom, although not over the full frequency range. Now let's try adding delay offsets between elements. This will effectively steer the lower frequencies but has a disastrous impact in the higher frequencies. The next approach uses specialized phase filters available in the modern world of digital signal processing. These filters can selectively delay a limited frequency range without affecting those above. This allows us to phase steer the low-mid beam without affecting the HF coverage. We're using targeted phase steering to reshape this limited range of frequencies into compliance with the HF range. Careful use of IIR filters in the low-mid frequencies can be used to either spread or steer the mid-low output of an array to closely match that of the higher frequency output. To successfully implement the steering, every element of the array will need its own signal processing channel and drive line, and low-mid EQ filters will need to be the same for all elements of the array. In the priorities of system optimization, steering of low-mids is not near the top of the list. For system designs with a mismatch between high-frequency and low-frequency coverage, using low-mid beam control to phase steer the low-mid coverage of an array to more closely match that of the high-frequency coverage is easily done. The result is a system that provides more uniform spectral coverage over the audience area. We can use MAP to determine how much a given design will benefit from LMBC. Provided we set the system up with the necessary wiring and processing, LMBC can be engaged and the results evaluated during optimization. Meyer Sound continues to develop and provide useful tools that are safe from unexpected side effects, proven scientifically, and practical to implement.